all components is extraction, liquid extraction. Here both phases are liquid phases, and so we need a slightly different representation. So the typical representation is in the form of equilateral triangular diagram, coordinate system. Right? So I don't want to go into the details, but this is the solute and this is the solvent, and following Raoult's notation. And so typically problem in extraction is I have a mixture of A and C, so that will lie on this side of the triangle. So what you have to notice here in this coordinate system is C is the pure component, solute, that is a solute. A is the other, or the, you can say not inert, but it's like a carrier liquid. Right? So C and A is a mixture, and we want to extract C out of the CA mixture by using a solvent B. That's the whole idea. And so you create two phases. One what is called as an A-rich phase, another a B-rich phase, and the solute distributes typically between both the phases. We obviously want a higher concentration of C in the solvent phase. So AC, the side AC contains all possible mixtures of A and C, starting from 0% A to 100% A. Similarly CB, similarly AB. This is just a coordinate system. Where is the phase diagram? Right? So the phase diagram, typically one of the common phase diagram is where the phase envelope looks like this. So what does it mean? Right? So it means that again, as in the case of distillation, there will be one phase envelope which has two distinct parts actually, you see. Right? So the phase envelope in distillation separates the two-phase region from the single-phase region. So same here. So everything inside this region is two-phase. This is all one phase. So what it means here is that if you take any mixture of A and C, it's in the single-phase region. So what it means that A and C dissolve with each other to form a homogeneous phase for all possible concentrations of A and C. That's what it means. Same with B and C. However, if you see A and B mixture, right? So everything I said enclosed by this envelope is two phase. So if I take a mixture, so let's say I have A here, right? This is pure A. So now I start adding B to it. So the overall composition of the mixture will start moving in this direction. More and more B is added. So the represents, let's say, this is 100% A and this is 100% B. I'm just moving along this line, so forget about the rest of the diagram. So clearly what this envelope means is that the moment I add, let's say I add enough B so that I am at this point. So what this means now is that this mixture will separate into two phases. One which is rich in B, another which is rich in A. So now what happens when you add C to a mixture of A and B, right? So let's say the overall composition. So now I start adding some C. So let's say I have reached this point. Now this is going to separate. And so now when I add C, it's now going to move because C represents the sort of the vertical direction here. Right? So we'll get to a point here, let's say. Now I have to specify how this mixture, which has A, B and C, is only the overall composition, how is it going to separate into two parts? So that is what is given by the so-called skyline. So the analogy here in distillation, let's say I take a constant pressure section. So I heat here, instead of adding C, I am adding energy. So that's the difference between distillation and extraction. If I have a mixture of acetic acid and water, let's say, I can add heat, liquid mixture, I can add thermal energy to it and create a new phase, vapor phase, and thereby I create two phases. Why do I need two phases? Because in one of the phases I expect acetic acid will be greater in concentration than in the other phase, so I've achieved a separation. Right? So here again I have a liquid mixture, so on adding energy it moves into the two-phase region. Here it's very clear how the tie line, I don't have to tell you how they have to be drawn, right? Because I know that the two mixtures, vapor and liquid, have to be at the same temperature if they are in equilibrium. So if I see that I have heated the mixture initially containing, let's say, 50% air, and I have heated it to this temperature, so I specify that only to you. So I know that now, let's say I have reached T star of this overall composition, nothing is added or removed. So clearly now it is in the two-phase region. So I know how to, this will be the composition of the X, and this will be the Y star of the vapor. That's very easy to do. Now here, now if you see, typically in extraction, both temperature and what is the number of degrees of freedom, right? So F is equal to C minus pi plus 2. So let's take for two-phase region, the system containing two phases, three components, two phases. Number of degrees of freedom is 3. So now there are these degrees of freedom, because only I have the composition on this diagram with no temperature or pressure. So both of the entire diagram is usually presented at a fixed temperature and pressure. In liquid the phase diagram will not have much effect due to the pressure, but due to temperature certainly there will be changes, and you can see there are many diagrams in Raoult which says how the whole phase envelope itself might shift, might become different, shrink or expand depending on the temperature, right? So that is something you have to keep in mind. So now, if I am fixing the temperature and pressure, so I have exhausted 2 degrees of freedom, so only one is left for two phases. Right? So now, what happens is that now I have to specify, so this envelope actually will be in two parts, and they are connected in through a tie line, what is called as a tie, what is called as a plate point, and so we have series of tie lines like this, let's say, and then finally this last tie line. So I have to give that. So what does the tie line say? Just as here, which point in one of the envelopes matches with the point in the other envelope, so that they are in equilibrium. Now here, unless I give you the information, it's not difficult. Tie lines will not be horizontal here necessarily, right? So these are the tie lines. So tie lines of information has to be given. So this is phase 1, let's say, and this is phase 2. So tie lines are given, then I can, so let's say my point falls here. So what this means that corresponding to this overall composition of A, B and C, this would be the composition of phase 1, this would be the composition of phase 2. So what it means is that now is the way with the 1 degree of freedom here, how do you interpret it in terms of the phase rule? That is our point. The point to be mentioned here is that when it is in the overall composition, suppose I fix a point here on one of the envelopes, right? Or let us say only 1 degree of freedom, so let's list out the variable TP. Temperature, pressure, this, and anyway, what are the other variables? Two phases are there, 3 components. So, one, the solute is as first, XC2, that means the mole fraction or weight fraction of C in phase 1 and that of C in phase 2. Let me maybe make it clear. I think what is normally chosen. Let's stick to phase 1 first. I can have XA, and then I'll have XC of 2 and XA choose XB. But typically solute composition is always chosen as one of the explicit mole fractions. Okay. So now these are the 4 variables, composition variables. And so there are 6 variables, 3 degrees of freedom. Right? 3 can be independently specified, but by fixing the temperature and pressure and giving you this diagram, I've already exhausted 3. So out of the 4 composition variables, right? Out of the 4 composition variables, only one can be independently specified. All the others are determined, right? So if I specify XC1, right, that means I can easily mark XC1, you know, the weight fraction will vary like this. I mean, the point is that if you draw the perpendiculars from each, you can move along that line and get various concentrations of C. So if you draw lines parallel to AB, you will get various. All the way I can divide this perpendicular or altitude into, let's say, 10 equal parts, and so I'll get 0.1, 0.2 like that. Right? I can mark this as a scale for C composition. So if I say XC1 is, let's say, equal to 0.2, and let's say that is this, right? That is XC equal to 0.2 line, let's say. So phase 1, right? So this is the phase envelope. So automatically its composition in phase 1 is fixed, because I have given you the phase envelope. That's part of the phase equilibrium information. Then I simply have to follow the timeline corresponding to that, and I automatically get the composition of the other phase. So clearly, the phase diagram, the way I have interpreted it, is consistent with the phase rule. Only 1 degree of freedom is there, and I can find all the other compositions. Right? So only one composition variable, once you fix the temperature and pressure, needs to be specified. Right? The 3 are found from the equations for chemical equilibrium, equality of chemical potential. There are 3 equations. You have to always check. The phase rule means that you set variables. 1 only can be independently specified. So I can fix this. Now I have to determine these 3. So you have to ask, where are the equations that would determine? Right? The equations are these. Equations are these, the equality of chemical potential, all the 3 components in the 2 phases. 3 equations, 3 unknowns I can in principle determine. Right? The remaining variables. So the diagram is certainly consistent with it. The way we find compositions from the diagram is certainly consistent with that. What about the other mole fractions? Clearly, once I know XC1 and XA1, the other XB1 is determined by the mole fraction constraint, which I don't include as a set of equations because I've already taken that into account. When I list the variables, I list only the independent mole fraction. So the other variables are automatically determined. So that's very important to keep in mind. Of course, there are other diagrams which you should look at in extraction, which for instance have this is A and AC mixture and BC mixture. Both are miscible in all proportions. That means they form homogeneous mixtures. You can have other types. For instance, you have some various other unusual diagrams are there. And this is another typical which you might have all seen. So here you can see that AC is homogeneous in all proportions, but not only AB, but again anything within this envelope is 2 phase. Everything else is single phase, right? And so we can see BC also can split into 2 phases after a certain composition. So you have to know how to interpret this. But those are all 2 components. You can also get a 2-component phase diagram in that, right? From this diagram. Are there any questions? Okay, now we move on to the calculational aspects of phase equilibrium. And for that we take up the variable equilibrium of a binary mixture. take arbitrary C component mixture and I introduce 4 important problems in vapor liquid equilibrium. So phase equilibrium, minor problems are there in humidification, absorption and all. I'll put them all in an assignment and give it to you. They are much simpler than what we are going to handle. This is really the most important part of the phase equilibrium calculation, which predominantly deals with only vapor liquid equilibrium, but it itself is quite extensive. So phase equilibrium, 2 phases liquid, vapor. Components, I can have C components. So we'll apply the phase rule. F is equal to C minus pi plus 2, which is equal to C minus 2 plus 2. C is a number of degrees of freedom. Now what are the variables? The variables are, I'll denote all the compositions, mole fractions in the liquid phase by X and the vapor by Y, and the subscripts will determine the component, the mole fraction of which component, right? So temperature, pressure, so I put x1, xc minus 1, xy1, yc minus 1. So how many variables are there? Number is 2 times c minus 1 plus 2 is equal to c variables are there. C variables, c is a number of degrees of freedom, so I must have c equations. Yeah, please. C equations, they are the equality of chemical potential. I am going to here represent them by the equality of fugacities. FIL is equal to FIP. The FIL I can be a function of TP and X is the mole fraction vector x1 of xc minus 1. This will be a function of y. So I have C equations, 2C variables. I have to choose C. Now there are many possible ways. In fact, you can see that there are so many C's here. There is a number of ways in which you can choose C variables. From 2C variables is 2C, C, C. So there are so many possible combinations, but only 4 important specifications. Because arbitrarily you don't want to select some composition from here, from some composition from there. Right? We can do that. It can be a good, interesting academic exercise, but typically that is not what is done. Practical calculation, there are 4 important types of calculations which I will list, and if you know what these terminology means, but whatever you do, you don't have any right to choose more than C variables. I can choose any possible combination from the 2C variables, but I can choose only C variables. So that's what the degree of freedom allows. If I choose more, then I am over specifying. If I choose less, then I am not specifying enough. So I won't have enough information to get the other variables. So you have to always keep that in mind. So the first problem is bubble pressure calculation. This will be the calculation of a pressure. When I say bubble pressure problem, it means calculation of bubble pressure. So pressure clearly has to be calculated. That's the way to remember. When I say bubble pressure problem, that means bubble pressure has to be calculated. So that means I have to calculate P. But what do I have to specify? Certainly I specify T. Yeah. Bubble pressure with T is specified, and what do you think is the mole fraction which would be specified based on our definition of bubble temperature and bubble pressure? X, right? So I specify temperature and The entire, I don't take a few mole fractions from liquid and few from vapor. That also I can do. But typically, the four important problems that are studied are, I specify the entire liquid composition. That means all the C minus 1, and in fact all the C variables are known. Right? Take to be C minus 1 are the independent. Of course, that C minus 1 has to add up, it certainly has to be less than 1. If you add up, you cannot specify, okay, I have a ternary mixture. So I say I have 0.1, 0.7, and I'm sorry, 0.1. Let's say I say 0.4 and 0.7. This is not allowed. So clearly, mole fractions cannot add up to more than 1. That constraint, you have to keep that in the back of your mind. This is not again arbitrary. Mole fraction constraint, all the C mole fractions must add up to 1. But you need to specify only C minus 1. Other is automatically known. Right? So I don't include that as a variable to be specified. You have to be very clear. So some books do that. But then you have to add the mole fraction constraint as an equation. So we are not doing, we might have to do it later. But right now we are not going to do it. So I have to now calculate the pressure as well as the mole fraction, the entire set of mole fractions, the vapor phase. Now you can very clearly see what the other three problems would be. One is the due pressure calculation. So again, this would mean calculation of the pressure. But here, clearly you can guess the other specification is that the vapor phase composition is completely specified. That is what is called the due pressure calculation. The other, bubble temperature. Here I have to calculate T, but bubble means I am specifying X. So this is what I have to calculate. Then 4, the due temperature. Calculation, again temperature I have to calculate, but here I specify Y. And I have to calculate X, the vector. These are the four important problems, and it is very important when a problem is given, because when you see in some cases the algorithms for some of the most general case probably the algorithms will all look very similar, but there are some special cases that we will consider. For instance, ideal mixtures, vapor liquid equilibrium, where you will see that the bubble pressure and due pressure calculation are much simpler than this. So when the problem is given, you should know what it corresponds to. Then you sort of get a feeling, okay, the solutions for the ideal case at least are readily available, something like that. Right? So you have to really map a given problem into one of these four categories. If it doesn't fit into it, of course that's a different matter. Okay? These are the four important categories. So now this is valid. We not considered any particular model for the fugacity. We are not even considered the number of components. Only thing is vapor liquid. And so it's very general. Now we will take a particular model. So the zeroth order model in vapor liquid equilibrium is the ideal vapor liquid equilibrium. In this, the gas phase is treated as an ideal gas mixture. So what happens to the, so this is a C equations are there. Let's look at the I equation. What would be FIP? Make it like this. That's how it's written. I don't really care which one you put on the left side and which one on the right hand side. But what would be FIB if the vapor phase is to be approximated as an ideal gas mixture? Partial pressure, right? So P YI. Now the zeroth order ideal vapor phase and the liquid phase is approximately treated as an ideal solution. I will say approximately because it's not exactly. Some further approximations we will do. Now, what is an ideal solution? Now, an ideal solution we saw, we defined it through the chemical potential. So an ideal solution is defined, a mixture can be called as an ideal solution the chemical potential of the ith component is given by the chemical potential of the pure component I at the same temperature and pressure plus RT. We have already seen. Now we want to convert this to a fugacity. What is the fugacity of a component I in the ideal solution? What is, do you think, how would you go about doing calculating this? What is the fugacity defined? How would you define the fugacity of any mixture, of a component in any mixture? P times Zi times the exponential of mu I mix. We always follow on the definition, a general definition. That is very important to remember the definitions. Now the portions for the quiz 2, since you asked, it will be everything that is covered until the previous class and what we covered about extract. No problem will be there on phase equilibrium calculation for mixtures. The pure components, it will be there. So whatever we have covered until yesterday's class effectively, today we discussed briefly about extraction. Interpretation of phase diagrams using the phase rule will be there. It's part of the syllabus. No phase equilibrium calculation for mixtures. Because pure components, we have looked at saturation pressure and various other calculations that were not really included in the first list. Those will be there. And I will explain clearly what are the topics you will have to focus on in tomorrow's class. I also announced the seating arrangement. Right? So tomorrow, but let's continue here. So this is what it is. So ideal solution, I just put the ideal solution. So I have to substitute that here. Right? So I have to substitute that and you will find, you can do the calculation, you can do the derivation, you will find that this will be xi. You have to prove it. How would you prove it? Because I have to bring the fugacity. Fugacity we know this will bring the ideal, this is the mu I of Tp plus RT log xi. So if we want to bring the fugacity of the pure component, this is where we have already seen how to proceed with the derivation. It's again a question of adding and subtracting. Right? So I will give you another chance to think. So if we want to bring the final answer is given, let's say, fugacity of the pure component. Now what should you bring into the picture, into the equation? Which quantity? The chemical potential of I in the, as in, what is the definition of fugacity of a pure component? That's a part of the quiz 2. You cannot say it is over. What is the definition? Fugacity of a pure component. Yeah, can you come and write fugacity of a pure component? You're supposed to remember these definitions. Yes, right. There are units of pressure that at least you should know. You have to remember the definition. You cannot say, go through a whole course on thermodynamics and say that the fugacity I find it very difficult. That's a basic quantity. You've seen how to calculate it using equation of state, using tables and so on. Fugacity of a pure component, F is equal to, answer is not there. It's P times exponential. I'm giving that. Yeah, what is within the exponential? You write that. Mu I minus mu I Ig. No, it's not mu I Ig. It's mu I minus mu I Ig divided by RT. It's related to the departure function of either the partial and the specific gives free energy or the chemical. Both are the same for the pure component. Right? Both. This is very important. The formula is not complete. That's why the same temperature and pressure. So we saw if it is the same temperature and volume, that's not the fugacity that we normally define. You cannot say that is the way I define my fugacity. There is no your fugacity and my fugacity. Only one fugacity that is defined in the standard textbooks. Right? So this is what it is. So if I am looking at the pure, this is mu mu I is not needed, but here it was not needed. Now I am isolating the C components in their individual pure component states, so I need to do this. So clearly, if I want to bring the fugacity of the component, then I have to add and subtract. And you will see, if I bring in the mu I ITM, that will have a mu I IT and all the things will cancel out and you will get this very nice explain. This is sometimes referred to as a Lewis-Randall equation or Lewis-Randall rule. The Lewis-Randall rule is simply approximate actual mixture by the ideal solution. So that's it. Right. So now here I have to put here xi, but what is referred to as the Raoult's law, which is what I am going to write, is not quite the ideal solution. Here, instead of writing fi of Tb, I put Bi san of T. So I am approximating further. So the ideal solution, first I can consider that liquid phase is an ideal solution, and on top of it, I am replacing fi. Then I get the Raoult's law. The Raoult's law considers the gas mixture as an ideal gas mixture. The liquid as approximately an ideal solution with the additional simplification. This is a big simplification because otherwise I have to use the equation of state to calculate the fugacity. But Pi san is readily available through the Antoine's equation and so on. Right? So it's more readily available. Right? So we reduce it from a function of temperature and pressure to a function of temperature. We have already seen in the case of humidification, when I replace the fugacity of the water by saturation pressure, what are the approximations involved? Pointing direction is neglected and sufficiently low pressures and so on. So sufficiently low pressure is already there in the when we assume ideal gas mix, vapor to be an ideal gas mixture. So it might not be a bad approximation. So where is it really applicable? What is the utility of this? This is clearly for ideal gas mixture. If you made, that means you have restricted low pressure. So the ideal solution is expected to apply to very similar boiling components like hydrocarbons in the same group and so on. Right? So liquid is similar or close boiling. They may be regarded roughly as ideal solution. That's the Raoult's law. But now, if you see here, there are of course C equations. Right? Because I equal to 1 to C. C equations are there. But however, I have, by how many variables are there apart from temperature and pressure? C variables are there, because by writing it as I equal to 1 to C, if I want to write it uniformly for all components, right, then I have to explicitly bring in all the C mole fractions. So if I want to stick to this, there's a subtle difference between what we consider when we specify variables and arrive at all this, then when we actually do the calculation. Now the option is, I will do it C minus 1 only, I will write it. So the C equation I will write it as P times 1 minus sum over P times YC equal to P C san times 1 minus I have to do it like that. Separate out the C equation, but normally that is not done. So what you do is, you prefer to, if you want to develop a code for carrying out these calculations, it's generally the procedure that is found to be more convenient is to consider all the C equations uniformly. Otherwise you have the C minus 1 you have to give in a particular form. The C equation you have to give in another form, right? That becomes cumbersome. So what you do is you keep this, but I see now the two additional variables I have introduced. So I have introduced two additional equations. those are clearly the now I have C equations plus 2, C plus 2 equations, and the variables also 2 extra variables I've added. So I keep the variables intact, the 2 independent, not non-independent mole fractions, but simply add the mole fraction constraints as extra equations. And you will see the important to these equations will be quite important. For instance, if I take bubble pressure calculation, automatically this will be satisfied. We don't want to deliberately specify something that not even satisfying the mole fraction constraint. That's absurd, right? So, however, you will see that the mole fraction constraint of y is also to be kept in mind. Sometimes it's not immediately verified. So you calculate the mole fractions of y and keep on with the algorithm and finally check whether in fact the calculated yi's. It's very important. You cannot afford to forget this. So for instance, due pressure calculation, you have to make sure that this equation is also satisfied, because sometimes the way the algorithm is written, you will directly be focusing on these and ignoring this for a while. But ultimately, you have to make sure that all the equations are satisfied. The mole fraction constraints will be an important part of the equations when you are calculating phase equations. While looking at the specification, it's better to ignore them rather than including 2 variables and adding 2 equations. At the right, at the outset in the phase group, typically they are not taken into account. But in calculation, the way it is constructed, those variables, non-independent mole fractions appear explicitly, and we account for that with the mole fraction constraint equations. So let's now take how the bubble pressure and due pressure are very easy to write down. The bubble pressure here for the Raoult's law, T and X are specified. So this important thing to know is that when T is specified, so both bubble pressure and due pressure will turn out to give explicit expressions for the bubble pressure and the mole fractions, right? Because of the fact that since a temperature is specified, this is completely determined. But if it is not specified, then it has to be determined only through an iterative procedure. So it's very important to keep in mind that for the ideal PLV, both these problems lead to non-iterative solutions. Very important to keep that in mind. The way it works is simply by adding these equations. Suppose let's say I have y we don't know. So I simply add all the C equations so that, and then use the mole fraction constraint. Right? So I simply add all the equations, then what do I get? E is equal to P times y1 plus P times y2 plus P times yc. Right? So P times y1 plus y2 plus yc, which will add up to 1. So I get P equal to sum over I equal to 1 to C xi pi sat of T. That's it. Bubble pressure is formed immediately. That is a bubble pressure. The xi is known and specified. X. T is also specified, because obviously gives an explicit expression for the bubble pressure. And of course, yi, which I don't know initially, can simply be easily calculated by xi pi sat by P. Of course, I can write the P is this, so here I write xj equal to 1 to C, xj Pj sat, I equal to 1 to C. Clearly, the mole fraction constraint will be satisfied because those equations have been obtained by satisfying the mole fraction constraint. So it's of no surprise that when you add these, clearly the mole fraction constraint will be satisfied. So it's very trivial actually, but you should know that bubble and due pressure give explicit expressions. Now what about the second? So this is bubble pressure. So the due pressure, again T is specified, but Y is specified and X is not specified. So what I do is, I don't add up the equations directly, but what I do is I write this as xi is equal to Pyi by Pi san of T. Okay, I always want you to keep remembering that Pi san is a function of temperature. Because here, that is where the explicit temperature dependence comes. When you go to non-ideal cases, that is one of the quantities which will have temperature dependence. So you cannot just treat it as a constant. So now I apply the mole fraction constraint. I equal to 1 to C. So if I add up now, right, so then I'll get P times sum over K equal to 1 to C Yj by Pj san of T equal to 1. This will now give me the due pressure. So the due pressure is sum over K equal to 1 to C Yj by Pj san of T, the whole thing raised to the power minus 1. That will give me the due pressure. So this is the bubble pressure, and this is the due pressure. So you can automatically write it. Once the specification is given, the due pressure can be found, and then the Yi, which we don't know, I'm sorry, the Y is known, the X, which we don't know, can easily be calculated by P times Yi by Pi san. Right, so this is will now look like Yi by Pi san divided by sum over K equal to 1 to C Yj. So here you have to multiply the mole fraction by Pj san, the liquid, and there you have to divide the mole fractions by Pj san, and then you will get the answer. So rather than remembering it, if you know the write the Raoult, you can simply add and get the, you should know what to add. Right? So here Y is not known, so I add the equations to use the mole fraction constraint on Y. In the second case, I have to use the mole fraction constraint on X. That's all. And I get the answer. Now when we go to due temperature, the first thing I notice, a bubble temperature, let's take the next one. Bubble temperature, first the temperature is not known. So I'm given only P and X. Temperature is not known. So if something is not known, you simply assume some temperature. So this will now involve an iterative process. So there are several algorithms available in the books. Numerically, we have to figure out which one is the most efficient. So let's take the bubble temperature calculation. First I see the temperature is not known and there seems to be no direct way of finding it. So T has to be assumed. So we take T to be equal to. What we will assume is it's open to question. But since these are ideal systems, right, and typically if you see, even for the binary case, the boiling temperatures will lie between the two pure component boiling temperatures, right? So we can use the same idea. So the bubble temperature here X is given. So good initial guess would be J equal to 1 to C Xj Tj, the boiling pure component boiling point of J. That might be a good, it might be a linear combination. Let's say only a zero, first guess bubble temperature. P is given. But at that pressure the pure common boiling temperatures are known. So for lack of anything else, I can start with this. Right? So we've run out of time. Are there any questions? Now we have to see how the algorithm proceeds. Right? And then, so given T naught, we want to know whether, so once T naught is given, then once I've taken the temperature, I can then find the PI sand, and then I can get a value for Yi. So that's what I will call as Yi naught. That is the Yi's corresponding to this T naught can be easily found, right? So it is found as Xi PI sand divided by P. So I have to make sure everything is known. But clearly there is no guarantee that this is actually going to add up to 1. Because I have not used that equation yet. Right? So one thing would be, one algorithm would be to check that whether the values are tight here. Because I have satisfied now these equations for this temperature. But there is one equation left which we don't know. So let's verify whether approximately, that means you have to set a tolerance. If yes, then I can stop. If no, then what to do? So how to choose the next temperature? So that I can go like this. So we have to see, as we have seen in any algorithm for saturation pressure, we start with an initial guess, and the initial pressure there was between the maximum and minimum pressures at the given temperature. Then we should know, once we have checked whether the fugacity of the liquid and vapor are matching or the maximum rule is satisfied. Then if it is not satisfied, we give a method by which we go to the next pressure. How to choose the next pressure? So you cannot arbitrarily say, okay, choose another temperature and keep on doing it. So we should know how to choose the next temperature. And finally, when we stop, how to stop, right? What is the criteria we need for stopping? We'll take that in tomorrow's class.